So in this first video, we need to learn the basics of statistics. Statistics is probably a different class from where you've been in math up to this point. You've probably done a lot of arithmetic and algebra and geometry. The statistics is a whole nother branch. So we need to get into the basics of statistics, and at the beginning learn some basic definitions, what the whole purpose of statistics is, and then we'll get into, over the next couple lessons, the nitty-gritty of it. And so we start off just talking about, sampling, data, and again, some basic terminology. So statistics, what is it? So statistics is the science of collecting, organizing, analyzing, and interpreting data in order to make decisions. Statistics is a scientific process. It's essentially what you would think of as a scientific experiment from start to finish. You have to collect and organize your data, you have to analyze that data, and then you have to interpret it. You have to say something meaningful. My approach to teaching this class is in two parts. One, we have to learn how to do the basics, in that we have to know how to calculate, organize, make graphs, do some basic calculations, mean, median, mode, standard deviation, z-score. These are all calculations we're going to do. And you need to learn how to do those calculations and get them correct. But the really important part is the last part, which is then interpreting all that information and saying something significant from that. And you'll see us progress through this over the course of the semester. The first part of the semester, we learn how to do the basics, collecting, organizing, analyzing, and the later part of the semester, we start to get really into the interpreting. If you can just calculate a value, calculate the mean, and give me the right answer, that's great. But then knowing what that represents and how to use it, that to me is most important. So I don't want you all to be a bunch of number crunchers and just pop out numbers and give me the answer. I want you to understand that answer and then to interpret that answer and to use it in order to make decisions. So something like this, if we were to write down the average times and hours for the nearest, to the nearest half hour that you would sleep per night, and then we record that data, we can create a simple graph to organize it. This is called a dot plot here. And so we look at it, okay, one night I slept 5 hours, another night I slept 5.5 hours, then a couple of nights in a row, maybe not necessarily in a row, but a couple of nights I slept for 6 hours, then 6.5, 7, 8, 9, etc. This is one, I collected the data in that I recorded how much time I slept each of the particular days up to the closest half hour. Then I organized it by making this simple dot plot, okay, and stacking dots over top of a particular number. That is the beginning part of working with statistics. Descriptive statistics. You're going to see we're going to be two parts of statistics we're going to talk about. One is descriptive statistics, where we do the first part, which is organizing and summarizing our data. We could do it with that dot plot that we just saw. We could do it with a bar chart. We could do it with a pie chart. But this whole step of descriptive statistics is about organizing and summarizing your data. That's going to be the first part of the semester. And then after that, we get into something called inferential statistics. And inferential statistics, you learn how to use that information you collected in the descriptive part. And we usually get to it once we talk about probability and probability distributions is when we're going to start getting into this. And you want to start drawing conclusions from the information you got. We start to see all your data plotted out. Can you draw some conclusion about what's happening with your data? And that formal method of doing this is called inferential statistics. So that'll be the second part of the semester, and probably more like the last third of the semester really is when we get into that, because it's going to take us a while to get through the descriptive part. So the general goal, again, is to not just, perform a bunch of calculations and using formulas and to get a particular value. Yes, you need to be able to do that, and you need to get the right answer, and we'll focus on that in the beginning, but really we want to gain understanding of our data, okay? We want to look at the calculations that are being done. We could do it on a calculator, we could do it on a computer. We're not really going to necessarily do a whole lot of math by hand necessarily. You're going to need a calculator to do this. You could also use a computer. Excel does a lot of this very easily for what we're going to do. But really we want to understand the information, okay? And in order to do that, though, you have to be able to do the calculations. And then once you have the basics down, we can really start to make these bigger decisions about the data. Probability is going to be something we're studying throughout the semester. Probability is a mathematical tool used to study randomness. Okay, it deals with the chance or likelihood of something occurring. We're going to talk about probability. We're going to talk about proportion. We're going to talk about percent. And in some ways, they're all tied together. So, an example, if you toss a coin 4 times, the outcomes may not necessarily be 2 heads and 2 tails. Okay, so you might get 3 heads and 1 tail. Okay, but let's do it 1,000 times. Okay, and toss the coin 1,000 times, or even 4,000 times, and record the number of outcomes of heads and tails. And what happens is here, we'll look at the probability of getting a heads or getting a tails, which is going to be 1/2 in each case. And the more times we perform the procedure, the closer we'll get to half of them being heads and half of them being tails. But if we did it only 4 times, we might not get 2 heads and 2 tails. If we do it 4,000 times, we'll get pretty close to 2,000 heads and 2,000 tails. But anyway, that study of probability is a pretty important part to statistics. And we'll get into that in the course of the semester. The reason why it's important is because statistics is really based off of probability. The theory of probability began with the study of games of chance, such as like poker or flipping a coin or rolling a dice. Okay, and these idea of these probabilities of these outcomes start to create predictions. And what we want to do is then use those outcomes to try to predict other things. Okay, or if we look at a particular situation, can we use it to predict future situations? And so, like, we want to predict the likelihood of, say, of earthquake or rain, whether or not you're going to get an A in a course. We can use probabilities to help us predict future events. And statistics plays a huge role into that. Okay, doctors use probability to determine the chance vaccination could cause a disease. That's pretty important right now. Or is it more likely to prevent a particular disease? So these all sound like different things in that you're talking about playing games or you're talking about earthquake or vaccinations, but the science and scientific experiments and statistics really are one and the same. And you're going to kind of see that here. So a couple of key terms here. One, population. This is an important one. In statistics, we generally want to study a population. Okay, population is the larger group that we want to study. Think of population as a collection of people, things, or objects, but it's the larger group. And we want to look at that population, we want to study it, and we want to say something significant about that population. There's a problem with that. Typically, populations tend to be very large, okay, and a little bit too cumbersome to work with. So if we wanted to say determine the population, say you want to know the average amount of money a first-year college student at, say, Rowan College would spend on school supplies that don't include books. So we randomly survey, 100 first-year college students. The population for this type of example would be all the first-year college students. It's a larger group. We didn't ask every college student, first-year college student at Rowan College, how much you spent except for books. We only surveyed 100 of them. But the one we're really trying to talk about here, and we want to look at how much money the average college student would spend overall, the population would really be all first-year students, as opposed to a sample. To study a population, oftentimes we want to look at a sample, and a sample is a smaller selected group of the larger group. So we take a small group, a sampling or proportion, a subset of the larger population. Those are the ones we're going to actually use to help study the population. Because like I said, if I was trying to find out how much money college students spend at RCSJ, I wouldn't be able to necessarily ask every single one. I mean, it's not an infinite number, but it's still a large number. It's hard to gather that data. So what I would do instead is take a smaller subset, maybe survey 100 students. And those 100 students I survey, okay, out of this question, if I determine the sample here, I look at the 100 students I surveyed, those 100 students are my sample. Okay, those 100 first-year students are my sample. And what I want to do is I want to use the information I get from those 100 students to then say something about the population, which is all the first-year students at Rowan College. And so this idea of playing between a sample and a population is extremely important. The way we do that is making sure that our sample is a good sample. And you're going to hear something called a simple random sample a lot. And what we're talking about is the sample accurately reflects the population. So it's much easier to work with these 100 students here and gather information from these 100 students than from all the students at Rowan College. And this is why we would prefer to use a sample as opposed to a whole population. But oftentimes we want to say something significant, not necessarily about the sample, but about the population, and we use the sample to do that. So a parameter is a number that is a property of the population. So if you did some sort of calculation for an entire population, that would what we call a parameter. Okay? So if you calculated the average or the mean of an entire population, that was what we would determine to be a parameter. Okay? But this is often hard to do. It takes a lot of time. Oftentimes when you're doing a full experiment, it could cost a lot of money to try and collect all that data. So we try not to do that. That's why we use samples. Okay? So if we were to determine the parameter, we want to know, again, the average amount of money a college student at Rowan College spends on supplies that don't include books. So if we randomly selected, 100 first-year college students, 3 of those students spend 150, 200, and 225. Okay, but what's the parameter? Well, the parameter is none of this stuff. It's the average amount of money the entire first-year students spend, right? So it's still the parameter is the average of all the first-year students. That's the parameter. As opposed to a statistic. A statistic is the number that represents the property from the sample. So if we looked at that same question and I said, okay, 100 first-year students, surveyed, and I found the average from those 100 students, the average from those 100 students would be my sample. Now, I hope that that statistic accurately reflects the parameter, because the statistic came from the 100 students. The parameter would be coming from all the students. Does the statistic reflect the parameter? And oftentimes, it should, and it will, but that's only if the sample reflects the population. Another key term is a variable. A variable, we usually use a capital letter, say X or Y, and it's just a characteristic that we're looking at, okay, for each person or thing in our population. So if we go back to the same question, all right, we're determining, the first-year college students here. The variable X is what we're basically looking at, and what we're looking at is the amount of money spent, okay, by one first-year college student. So some random variable X that we could call is what we're studying. We're studying the amount of money. So our variable is that. As opposed to the value of that variable, and that's a little bit different, okay? So first off here, variables can be numeric, they can be categorical. We're going to focus more on numerical variables here because in a first-year statistics class, that's usually easier to work with. They're equal units such as weights in pounds, time in hours. Okay, categorical variables place the person or thing into a category, obviously. So, you could say like colors of cars or something like that. Or in this case, we let X equal the number of points earned by one math student at the end of the term. That would be numerical. But Y be the person's party affiliation. So they're Republican, Democrat, Independent. Those would be your categories. But again, X just is the particular thing you're studying about the population, as opposed to data. I've said data a bunch already, but data is the actual value that the variable holds, okay? So in this case, $150 is the amount of money one particular student spent. That would be the data value, the value of X, which is the amount of money any student could have spent. Okay? So 200 would be another data value. 225 would be another data value. So we broke our data into really these two types, qualitative and quantitative. Qualitative is the numeric value, and qualitative is the categorical value, and quantitative is the numerical value. And so, looking at, whether we're talking about the amount of money someone spent on something or what their party affiliation is, would be the difference between qualitative and quantitative. Qualitative is categorical, quantitative is numeric. And again, qualitative data is categorizing things, so hair color, blood type, ethnic group, car, a person drives, etc. Those would be all your qualitative things. We're not going to do a whole lot of qualitative data this first semester. Quantitative data are numeric. Okay, and this is what we're going to study a lot. So we're going to look at things like money, pulse rates, weights, number of people living in your town, etc. And we're going to study this quantitative data. We also break it into two groups, discrete and continuous. So again, numerical value is broken into discrete and continuous. So it really is the difference. It's important to understand the difference because how we study these two things will change the methods we use. So all data, okay, that are discrete data is essentially what we call countable data, okay? Data that you could easily count. Let's say with, one of those clickers you use to count people coming through a door for a particular event. If you can count your data using one of those, then we would consider that to be discrete data. Okay, so something like if you count the number of phone calls you receive each day, you can count that. So you get numbers like 0, 1, 2, 3, etc. As opposed to continuous. Continuous, we don't say it's not countable, but what we basically say is that there's infinite number of possibilities. Okay, it's a continuous data set, and so the more accurately we could measure the data, the more values we could get in our data. So like you and your friends are carrying book bags with books in them to school. All right, if you counted the number of books in your bag, that would be a countable number. And you would do that with a clicker. However, if you wanted to look at the weights of each one of your book bags, that would be when we talk about continuous. It's a large scale, infinite number of possibilities that could be counted infinitely many ways depending on our precision of weighing those bags, and most likely we'd use decimals to represent it. So usually things like weights, heights, things that are measured on a scale would be considered continuous data. And understanding which one you have is important because how we study it will make a difference, especially when we get to something called probability distribution. So here's another example. You go to a supermarket, you purchase 3 cans of soup. One's 19 ounces, it's tomato bisque. One's 14.1 ounces, it's lentil. One is another 19 ounces, it's Italian wedding soup. You get 2 packages of nuts, peanuts and walnuts, 4 different types of vegetables, 2 desserts. And so we want to look at this and say, well, which one of these are quantitative and qualitative? And then if they're quantitative, which ones are discrete and continuous? And so if we go through it, we said, all right, well, the 3 cans of soup, 2 packages of nuts, 4 kinds of vegetables, 2 desserts, they're all quantitative discrete data because we can count them, okay? So it's the number of soup, the number of nuts, the number of vegetables, they're numbers, so quantitative, and they're discrete because we're counting how many of each we have. If we looked at the weights of the soups, 19 ounces, 14.1 ounces, and 19 ounces, that's numeric, so quantitative, but it's also continuous in that it's a measure of weights. It can be done as precisely as we want. So do we do it to 1 decimal place, no decimal place, 10 decimal places? It would be measured on a scale. So there's a continuous amount of values, an infinite amount of values that they could be, and so that would be our continuous data. Now, just the types of things you bought, say soup, nuts, vegetables, desserts, that would be considered qualitative data, in that those are just different categories of food. So that kind of breaks down all those different types of data that we just talked about. Here's another example. If we looked at these things and said, okay, well, what do these fall into? Okay, so the number of pairs of shoes, type of car you drive, etc. So looking at this number of pairs of shoes you own, that's countable, so that would be discrete. The type of car you drive, that would definitely be qualitative. Okay, the distance it is from your home to the nearest grocery store, that would be continuous, because that distance could be very precise and measured in some scale. Okay, so that would be your quantitative continuous. The number of classes you take per school year, okay, that's a number, so quantitative, and will be discrete because you could definitely count those. The type of calculator you use, well, that's a group there. That's not a numeric value, so that would be your qualitative. Weights of sumo wrestlers, definitely numeric, so quantitative, and definitely continuous. Okay. Number of correct answers on a quiz, again, countable number, so we would say that that would definitely be your discrete. And then finally, IQ scores. That one could kind of go either way here. If you have to know how to calculate an IQ score, but I would say that that would be on a scale, scoring wise. If you wanted to really get precise in looking at how someone's IQ score is, you could say that that would probably be a continuous scale, and that would be quantitative. So continuous quantitative. We're going to get used to displaying our information. We could look at just a bunch of numbers on a page, but what would be probably more important would be how we display it in a table or a graph. We're going to look at organizing our data in graphs and tables, okay? And that'll help us give us better understanding of our information. So I could calculate how many people are full-time, part-time, and I could just write down those numbers, right? But if I put it in a table like this, I can really get some information about it. And I can look at the raw numbers, and I can also look at it as the percentage of people who fit each category. And I think oftentimes percents help people understand things a lot better. And so if you said 40% of our population was full-time and 59% was part-time, people would understand what those numbers mean. If you said just 9,000 people are full-time and 13,000 people are part-time, I think that wouldn't mean a whole lot to you other than there's more part-time than full-time. But by converting them to percent, sometimes it's easier to make some more general statements about the particular data values you're studying. But putting in a table makes it easier for us to see this, and then also makes it easier to compare two different data sets. So I can look at two different colleges, and I can say, oh, this college has 4,000 people full-time, and this college has 9,000 people full-time. Clearly, there's more here than here, but really what matters is how it compares to the total number of students, so the percentages are really what you would want to do to compare both sides. Just because one has more than the other doesn't mean it's got a larger percentage in that group. In this case, it follows suit. Again, pie charts, instead of just a basic table, you could use pie charts to describe things. I think people identify more with the visual than the raw number values of things. So this is a good way to display your information. And simply a pie chart would just come from putting your stuff into a table here. Oftentimes when you put your information into a table, it doesn't really add up to 100% depending on what you're looking at. So look at this one, full-time students, 40.9%. Students who intend to transfer to a four-year educational institution, 48.6%. Students under 25, 61%. None of these are mutually exclusive in that some students are in multiple categories. So what happens is if you were to add up these percents, they're not going to add up to 100%. You're going to get more than 100%. So trying to do this as a pie chart doesn't really work necessarily based off of whatever this study is talking about. So we would not necessarily do this as a pie chart. When you use a pie chart, you really want it to be based off of all your values being mutually exclusive in that they don't overlap. But because some students can be full-time and be transferring to a four-year university, and be under the age of 25. They're in all these groups. One single pie won't handle this. So instead, we would use a bar chart maybe to describe what was happening in that information, okay? And to look at how many people fit into each group, because trying to fit this into a pie wouldn't make sense. They would all be their own pies, essentially. So making them their own bars would be best. Again, when we use a pie chart, we want to make sure we're working with 100% here. So if we're talking about ethnicity of students, we want to cover kind of everything, and then you use the other category to kind of fill out the pie. And then you can compare that between two separate things. How you organize your pie really makes a difference here. Lots of times doing it from like biggest to smallest instead of randomly putting pieces in there could be helpful in that it can kind of direct the person looking at the pie to the appropriate information. So when you organize your pie chart, oftentimes this second one is better to organize your wedges in a way so that each one is done from, say, like smallest to biggest instead of randomly selected around. Bar charts could be done the same way. We could do a bar chart where we just have random bars, but you could also do a bar chart where it's done from greatest to least. When we do that, when we take just a bar graph that could be any order, and we do it from greatest to least, we call that a Pareto chart, okay? So a Pareto chart has always this sorted from largest to smallest, but it's still just a bar chart, but in that particular order. But nonetheless, you know, the bar chart and the pie chart, two ways of describing your data. All right, so when we get to sampling our information and finding our sample, we really want to make sure that our sample is an accurate sample. So when we gather information about an entire population, all right, we want to make sure we do it accurately, and oftentimes it's too hard to do it for the big population, so instead we'll use a sample. The sample has to have the same characteristics as the population, otherwise it's worthless. So we want to use different ways of doing it, but the key is we want to do random sampling to ensure that our sample reflects the population. And there's a lot of ways to do this. You'll hear simple random sampling as a way of calculating a sample. You'll hear this term a lot. It's pretty straightforward, okay? It's just make your sample created as random as possible. You could use a random number generator to select values. So if you're looking at heights of people, assign each person a number and use a random number generator to do that, okay? We could do that. If he said Lisa wants to form a 4-person study group for a pre-calculus class and that has 31 members, to choose a simple random sample of size 3, let's say, from her classmates, she puts all 30 names into a hat, shakes the hat up, closes her eyes, picks 3 names. Well, that's pretty random, right? That's the most random you can get. And another number generator could do the same thing. You could use calculators to do this. You could use computers to do this as well. The hat is a pretty crude example of it, but it works the same way. Okay? So something like this, you identify each person with a number, and then you randomly put that into your calculator, and it'll output a bunch of random values. And those would be the 4 people, or if you chose 3 people, or whatever that would be in your sample. So that's what we call a simple random sample, okay? We could do it with a much larger group, you know, again, random number generator, and we could just look at some random value here in a random number generator and use that to identify our students. Stratified sampling, okay, is a little bit more involved than that randomness of simple random sample, but still we try and keep the randomization there. So stratified sampling is when you divide your population into groups first, okay? They're called strata. So let's say we have males and females, or something where we have first, second, third, fourth year students. And then what we'll do is then we'll randomly pick from each group. So the 3 students randomly from the first group, 3 students randomly from the second group, etc. And sometimes we do that because we want to make sure we have the same amount of men and women in our study, or the same amount of first, second, third year students in our study. So here's an example. You know, you stratify your college population by department. So you say, okay, how many people are math majors, how many people are science majors, or even if you want to go STEM, liberal arts, health sciences, etc. Whatever, you break them into those groups. And then if there are 5 departments total, okay, you want to choose a sample of 50, we'll randomly pick 10 people from each. How? From that simple random sample method. You can just say, put them in a hat and pick 10 people out. Use a random number generator and pick 10 people from each one. But at least now we make sure that we have the same amount of people from each department. So there is some organization to how you're collecting your data, your sample, but you're still trying to use randomness as well. And that's called stratified sampling. Cluster sampling is somewhat similar to that. You divide your population into groups. So maybe you do this by neighborhood is typically a good way to do this. So you put each sample, each group of your population, based off of certain neighborhoods, and then you pick from there. So here's an example. If you randomly sample 4 departments in your college population, the 4 departments make up the cluster sample. Divide college faculty by department, then the departments are the clusters, number of each department, and then choose the 4 different numbers. So the idea here is that you randomly selected 4 departments. You didn't say, okay, I'm going to divide my group. The difference between stratified and cluster sampling is you don't have them split into each group. Here what you have is you randomly picked your groups, then you divide that by the departments, by those groups you randomly picked, then you randomly pick from those. So you're not necessarily going to get all the departments in a particular college population. You're picking a smaller group from that and then picking from that group randomly. Systematic sampling is where you look at some starting point and you pick like the nth value. So if I was walking up and down the rows in the parking lot and say, I'm going to look at the cars that people drive in terms of the color that the car is. What I'm going to do is I'm going to pick every 5th car and I'm going to record the color. So I'm going to walk up and down each row, every 5th car, that's the color I'm going to choose. That's systematic sampling, where you pick every value and you're going to, from some random number, and you're going to collect each one of those. Here, as a phone book question, a phone book has 20,000 people in it. You want to choose 400 people. So what you're going to do is you're going to pick some random number and you're going to say, I don't know, how about every 50th person? I'm going to go through the phone book, and every 50th person, that's the person that's going to be in my group. So if you keep adding that up, out of 20,000, you should get to your 400 names. So that's your systematic sampling. It's pretty easy to do. Depending on how the things are organized from the start, it still is pretty random. And you can get a pretty good sample out of that. Convenience sampling is probably one of the worst things you can do. If this would be done, say, if we were doing some sort of survey, okay, and you were looking at, say, potential customers or maybe people, on a college campus, and you only asked people that were easy to ask a question to. I want to learn something about the population of all college students in New Jersey. And so it's convenient for me to ask Rowan college students a question because they're on my campus. It would be a lot harder for me to travel to all college campuses around New Jersey. So convenience sampling for me would just to take my sample from this college's campus. But does that accurately reflect the entire population of all campuses in New Jersey? No, not necessarily. Is it random? Yeah, I was going to randomly pick, people that I walk past and ask them a question, but it's not the best way to gather information because I'm only doing it in a way that's convenient for me. So probably one of the worst ways of sampling. You still have some randomness involved, but not something that's the best method. One thing we look at is whether we're going to test with or without replacement. So, if you're truly making a random sample, you usually do it with replacement, which means if you take something out of a group and use that as a data value. You then put that data value back into the larger population before you randomly pick your next value. Now this has some problems to it. Now the problem with that is, yes, it's random, okay? You're making the randomness, work out in your benefit every single time, but you have the chance of taking the same data value out again the next time around. So I use cards as a good way to describe this. I'm going to randomly select 3 cards out of a deck of cards. Pull the first card out, look at it, record what it is. That's my first data value. Put it back into the deck of cards. That's with replacement. Then I'm going to pick another value out of my deck of cards, another card out of my deck of cards. Look at it, record what it is. But there's a chance that that second card could be the first card again. So I have a King of Hearts, say, the first time, and then I have a King of Hearts the second time. Well, that doesn't really help me too much in collecting my data if I keep getting the same data value over and over again. So oftentimes, to avoid having that happen, we do without replacement. So, we'll pull a card out of the deck of cards, put it off to the side, pick another random card out of the deck of cards, put that off to the side, etc. Or if we're asking people a question, we'll ask someone a question, record that answer, and then we're going to make sure we don't ask that same person a question again. So we put that person off to the side. And if they happen to walk past us again, we're not going to just go ahead and ask them the same question again, just because they randomly were the 10th person that came by a second time. We're going to say, all right, well, we're going to ignore that. Let's go on and go to the next person. And that would be without replacement, okay? And we're not going to put the person back in. So, for convenience sake and to make sure that we don't get a lot of repetition in our data values from the same source, we often would like to do without replacement. But for really truly going with randomness, with replacement is the most random way of doing it. Okay? There are errors that occur. Like I said, with convenience sampling, there could be errors that come in. We got to understand that not every sample will be perfect, okay? And sometimes our samples will not be big enough. Sometimes our samples will not accurately depict the population. And sometimes we don't find that out until we get to the very end of a whole statistical analysis. And we decide, oh, wait, this sample may not have been the best sample that we thought it was. And so understanding that that could happen is important. How can we avoid that? What we want to do is we want to make sure our sample accurately reflects the population. One way to do that is the larger the sample, the smaller the error will be. If I have a sample of only 3 people, there's a chance that I cannot reflect the population of, say, everyone in New Jersey. If I have a sample of 3,000 people, I'll probably have a better chance of reflecting what happens for the whole population of New Jersey. If I have 1 million people, then I will even better have a chance of accurately reflecting what's happening in the population. The problem is you don't want your sample to get too big, in which case then it becomes just as large as the population and too cumbersome to work with. So there's got to be some happy medium. We're going to try and find that. So make sure your sample is large enough, but not too large. And you want to make sure that you can accurately reflect the population. But there will be errors that occur. Not every sample will be perfect, and we need to understand that. So a couple of things, we want to look at when we're trying to evaluating statistical studies, okay? That there are problems with samples, that's going to be important. Self-selected samples often are not that great. Sample sizes can be often too small or unreliable. Sometimes there are influences that when we collect our data that could change the way our data develops. Sometimes you ask a very controversial question. If you do it in person, people might answer differently than if they were anonymous. So you worry about sort of the undue influence. When people don't respond or refuse to respond, how do you use that in your collection process? Does that mean anything in your data evaluation process? Make sure that you're looking at who's funding a particular study, because that could definitely affect the outcome. Some people could use their funding method to sway the collection and therefore the outcome of the data. Reading data incorrectly, so using misleading graphs or charts to portray some information that is not necessarily correct. One thing you've got to understand as a statistician, you want to present the most accurate, non-biased information possible. And funding problems, misleading graphs, marketing ploys, these are things that we don't want to get involved in when we're doing statistical studies. All right, finally, we want to look at some basic experimental design and ethics issues, and then finish this. So, experiment. Experiment is basically the entire process of a statistical analysis, most of which we've talked about already. So, does aspirin reduce the risk of heart attacks? Okay. Is one brand of fertilizer more effective at growing roses than another? Is fatigue as dangerous to a driver as the influence of alcohol? Right? These are all big questions. And the process of answering any of those would basically be a statistical study. We would collect some information, right? Maybe it's about aspirin and heart attack risk. So we look at who took aspirin, what percentage of those people had heart attacks, people who didn't take aspirin, heart attacks, etc. And we would collect that information. We would first create our sample, collect that information, then we'd study that information, okay, calculate some basic calculations, organize it, and then we'd make some general statements about all the stuff we've done. So we would go through this whole process, okay, till eventually we come out with a final result. And what is the final result? Okay, what do we get in the end? And so that whole process is an experiment. It's a statistical study. So the final important thing is when you're doing these experiments, ethics needs to play some sort of role here. Okay? So the U.S. Department of Health and Human Services oversees federal regulations of research studies with an aim of protecting the participants. When the university or other research institution engages in research, it must ensure the safety of all human subjects. There's got to be some sort of ethics involved here. You cannot perform an experiment on a human being, okay, one, without them knowing it, two, without them knowing what the possible outcomes could be. So there needs to be a certain amount of ethics involved in your experimentation, in your study. So you have to know risk to the participants must be minimized, and they need to know what is happening to them, so they must be given informed consent. So they have to know what the risks are. The subjects must consent in writing so that you then have proof that you told them what the risks were and that you've minimized the risk, but they still know what the risks are. And then the data collected from those individuals has to be protected. You have to make sure that that information is private. So all these things are the ethics of a statistical analysis and an experiment that you need to make sure are followed if you were to move forward with statistical analysis.